Bismillah ar-Rahman ar-Rahim. Natural exponential functions. It's a form of a non-linear change encountered in medicine. To simplify, is the process during the process of filling a tap. Suppose the water is running in a laminar flow, and we can see by time that there is a relation between the volume and time. This relation, of course, is linear. But on the other hand, if we open the plug hole, which is at the same level of the water, and we let the water descend, first of all, we'll find that descent is in a speedy way, and then it goes slowly after that, creating what we call the exponential curve, as you can see. This curve never reaches zero, you see. So simply speaking, correlating the volume and the pressure and the flow with each other, we can say that the flow is proportional to the pressure, and the pressure is proportional to the volume. Of course, whenever I increase the volume, the pressure increase. So the flow is correlated to the volume. In other words, if we want to define the exponential function, we can see through the curve the rate of change of the quantity at any time is proportional to the quantity at that time, you see. So whenever the quantity is high, we have a high rate of change, you see. So this is the explanation of exponential. Now we come to what we call wash out curves. What's the meaning of wash out curve? Suppose we increase the muddiness of a tap full of mud, and this mud is even distributed, must be even distributed, and then we open the plug hole. So the mud will come out through the plug hole, first of all, in a speedy way. In other words, the amount of mud which is present in the beginning is correlated, of course, to the concentration of the mud present at that time. So this is an exponential method. Of course, I can estimate the quantity of the mud by multiplying the volume of the tap by the concentration of the mud. So this is an exponential function which we utilize to measure the cardiac output. In anesthetics, the washout of tissues by suppose an indicator is as if I had filled the chambers of the heart with mud, and I'm beginning to clean up this mud. So the first method to measure the cardiac output is what we call the green indicator. We call it indocyanine green, where we inject via a catheter into the right heart. The concentration of the dye is going to be measured by a spectrophotometric method through a peripheral vein, and it's going to be, the concentration is going to be plotted against time, you see. First of all, the dyes increase, and it becomes and decrease again exponentially, and then after that it causes a hump because there is a recirculation. So of course, to get rid of this hump, we use what we call a semi-logarithmic curve, where the transverse is linear and the vertical is logarithmic. So this is why we call it semi-logarithmic. So we can remove this hump if we extend this curve downwards till we reach to below the level of the vertical line, because this line is not in zero. You must put in your mind this line is not in the zero, so that whenever I want to reach the proper measurement of the curve, I must extend this line beyond the level of the vertical to reach zero. This is why we must put in our account during measurement of the cardiac output by using the indocyanine clean, where we use the amount of drug injected over the area under the curve, you see. Of course, whenever the cardiac output is rapid, of course, the washout is in a speedy way, as we can see. This is the indocyanine green. On the other hand, we have what we call the the thermodilution method, where we inject around 10 cc of 5% dextrose in approximately 0 degree through the right ventricle, the connection between the right ventricle and the inferior and the superior vena cava. Of course, we can use two casters, or we can use what we call the Swan-Ganz caster, which is made of several ports. And then we inject this. While we are injecting this cold solution, while it's going through the pulmonary artery, definitely it will warm. So it will create an exponential curve. This exponential curve, first of all, it's not as one we know, because it is in a reverse direction, because we're increasing, not decreasing the amount, because the temperature has been increased. This is why sometimes we can reverse this curve in a way so that it will look like the exponential or the negative logarithm exponential curve. We have what we call the index parameter nitrogen. Of course, nitrogen, whenever we expire nitrogen, we can get rid of the amount of nitrogen from our lungs, where we keep only 2.5% of it after several minutes. Of course, if we fail to do that, that means that something's wrong with our respiration. This is a washout also. Of course, the washout technique, I'm sorry, the radioactive decay is also a method of washout. The duration of exponential process, but it is in a negative. We call it negative exponential process. Of course, the half time is the time taken for the quantity Q to fall to the half. You see, it's using radioactive isotopes. And then we have what we call time constant or rate constant. It's the time which the process would have been complete had the initial rate of change continued. We are assuming some. By Greek work, it's called ta. It looks like the T. After one time constant, the quantity falls to around 37% of the value. So it is more than the half time. Suppose the time constant of expiration is around 0.3 seconds. So after 3 time constant, or in other words, after 0.9 seconds, around 5% of the tidal volume is left in the lung. This is the normal washout of nitrogen. So we can estimate the ta through multiplying the compliance in the resistance. We know that the compliance is half liter per kilopascal per liter, and the resistance around 0.6 kilopascal per liter. If we multiply both of them with each other, we reach to the time constant we had figured it out. Of course, the time constant of a wash-off curve can be estimated by dividing the volume of washing under the wash out under the curve over the flow of perfusion fluid. The radio isotopes, of course, decay can be estimated through the washout technique by scintillation. The exponential formula, of course, any exponential formula is made of x to the time of. You see, this is constant. This is a way we can create a straight line. But on the other hand, the exponential function, which we encountered in medicine, is not constant. So we write it y equals k to the power of x. X is x X is the changeable exponent. You see, k is not known to be equal to 2.718. So we represent it by E. So we have an equation here. This equation gives me a hint about what happens, or how can we predict the volume of the lung at any time. So we make this equation using the resistance and the compliance and the volume of the air above the functional residual capacity, and the volume of the air after 1 second and at 0 second. This is a negative exponential. Of course, the volume is decreasing. This is a way where we can notice the amount of volume in the lung at any time. The positive exponential process, of course, this how does it look? whenever I grow a bacterial and special nutrient, and we call it an explosion exponential. So see how it goes upwards in a different way from the normal exponential curve. Now we come to what we call the positive exponential process. We can see what's the meaning of the positive or the build up exponential curve. It is not like the positive exponential curve. It looks in this way. It's different from that of the positive exponential curve. So this is built up, as you can see. So this is our example represented how do we have a head of pressure between this compartment, and this is how the fluid going from this compartment to the other through a plug hole, as you can see. And this is the way how whenever I use a constant pressure generator, means that the pressure is constant throughout the process of inspiration, but it creates a positive or an inverted negative exponent. You see exponential curve, built up exponent. This how does it look whenever I use a constant pressure generator. Considering how does the anesthetics work, of course, whenever I inject anesthetic the human being, of course, it undergoes built up, and then it goes from the lung, it goes after that to the circulation, after that it goes to the tissue, after that it is being eliminated. All these are exponential processes where we can represent it by an exponential curve, as we see, but each inclination of it can be extended to special lines. These lines can give me ABC lines. Each of them are being examined to represent the attitude of the drug, the anesthetic drug, in suppose 2 or 3 compartment model. We call this build-up exponential wash-in curves instead of the wash-out curves we had mentioned before. This is the way how do we, whenever I inject a drug through the oral cavity, absorption, of course, is exponential. Of course, first of all, the drug concentration is high, so it goes in a speedy way, and then it slows. And when the plasma concentration is increased, it goes to the tissue in a negative exponential measure, and so forth. So we ought to keep the level of the plasma in a way to keep the optimum dose of plasma to achieve our target regarding the patient. Or we can use syringe pumps or infusion pumps. This is a hint about natural exponential functions in medicine. Wassalamu alaikum wa rahmatullah wa barakatuh.